Now let's discuss SELinux implementation. This section will serve as an introduction to the way SELinux is implemented within Red Hat Enterprise Linux. So let's label this section SELinux Intro, and we'll describe some of the features provided by this powerful way of securing your Linux system. SELinux restricts access by subjects to objects. So it restricts access by subjects, and subjects can be users and or processes, such as programs running on your system like the Apache web server, to objects, and objects are basically files, which includes directories, standard files, devices, or any type of file. It does so by primarily implementing mandatory access controls. So it provides mandatory access controls, or MACs. And MACs, or mandatory access controls, extend DACs, or discretionary access controls, which all Linux systems ship with. So MACs extend discretionary access controls, or DACs. Now you can think of DACs as standard Linux Unix security, which allows you to apply permissions using 9 bits to an object such as a file or a directory. So DACs are basically standard Linux permissions. And with MACs, or mandatory access controls, we get to extend the model, enforcing a stricter security set. Now, SELinux does so using the extended attributes supported by file systems in Linux. So stores MAC permissions in extended attributes of file systems. So basically, SELinux provides a way to separate users, processes, and objects, or subjects from objects. So it provides a way to separate users, processes, which are both subjects and objects, using a technology known as labeling. And the labels per object as well as per subject are stored within the extended attributes of the file system that you've implemented on your Linux box, whether it be Riser, ext2 or 3, and so on. And it does this labeling and monitors and controls their interaction. So it monitors / controls their interaction, and by their interaction we mean interaction between users and processes, also known as subjects, and objects, such as files, all types of files. Now, depending on the user or the subject that you are, the permissions or the label assigned to the subject that you are or the process is will determine whether or not the subject, user, or process has access to a given object. And that's controlled through labeling, and SELinux, which is embedded in the kernel, integrated into the kernel, controls the interaction. Let's just note that SELinux is integrated into the kernel. And the kernel references a matrix of rules to make the determination as to whether or not to grant access to various objects to various subjects. In addition, more higher level thinking, SELinux implements sandboxes. So it implements sandboxes for subjects and objects. And the default Red Hat Enterprise Linux implementation, so default RH5 implementation, creates sandboxes for targeted daemons and one sandbox for everything else. So basically with RH5, certain daemons such as NTP, HTTPD, and others are sandboxed. They have their own operating spaces and they cannot leave their space to interact with another sandbox. So Apache cannot interact with, let's say, the sandbox of the Network Time Protocol service or another protected service such as NNTP, and so on. Everything else, for the sake of compatibility with standard discretionary access controls provided by Linux, gets lumped into the general purpose sandbox known as the domain unconfined T. So these sandboxes are known as domains. And one sandbox is again reserved using the targeted policy known as unconfined T for everything else. So members of unconfined T, which includes standard users and non-protected or non-targeted processes, operate within the major sandbox unconfined T. We should also note that it's implemented by default. So implemented by RH5 by default. And by implemented we mean SELinux. So SELinux is implemented / enabled by default. It also operates in multiple modes. As you can see, there are numerous features. Operates in the following modes, including permissive, enforcing, and disabled. Disabled is self-explanatory. SELinux is not enabled. And as a result, your system operates like a standard Linux system, meaning only discretionary access controls are enabled when SELinux is disabled. Enforcing enforces the rules defined by the targeted policy or any other policy that you may be using. So, strictly enforces targeted policy rules, which is the default and supported policy that comes with Red Hat Enterprise Linux. The same applies for version 4 as well. So if you want to learn more about SELinux, you can consult Linux CBT SELinux edition, where we study SELinux as it applies on Red Hat Enterprise 4. And there are minor to no differences between the implementation on 4 versus 5. Plus or minus a few tools, a few conventions, but by and large it's the same technology. So again, SELinux operates in the following modes: permissive, enforcing, and disabled. Disabled means only DACs are applied, meaning standard Linux permissions. Permissive, however, is slightly different. Permissions are granted when permissive is enabled. So let's just note, permission is always granted. However, denials are logged in the standard log file, var log messages. So in other words, permissive gives you an opportunity to debug, to fine-tune, and to determine if SELinux would object to the actions performed by the daemons, as well as other types of subjects, users, on your system, attempting to access objects, of course. So the subject-object interaction. So permissive is the way you want to go if you're simply testing SELinux compatibility. But these are the modes: permissive, enforcing, and disabled. And these modes may be applied upon system startup or while the system's up and running. So modes, or operating modes, can be applied upon startup or while the system is running. And upon startup, in order to enable or disable or to alter the actual mode, whether it's permissive, enforcing, or disabled, that SELinux operates in, you pass in options to the kernel, which we'll look at momentarily with our box Linux CBT Serve 4, and it disables it altogether. We should also note that when in permissive mode, permission is certainly granted, denials are logged. However, the denials are a result of the SELinux kernel interface consulting the Advanced Vector Cache, or the AVC. The AVC maintains the various policy information, the targeted policy information, and operates based on the targeted policy rules. So it's essentially your access control list, the policy which defines whether or not a subject can interact with an object in a given way. Now there are a number of tools included. Let's just list config files and tools, including but not limited to SEStatus. SEStatus displays the current status of SELinux. So displays current SELinux status. Let's go ahead and try to execute this on our remote system, Linux CBT Serv 4. We could also execute it locally as root, but let's SSH as root over to Linux CBT Serv 4 because the remote system has been the object of many of our lessons. So that said, SEStatus, and which SEStatus tells us that it's to be run by root because it's in user SBIN, but it tells you whether or not SEStatus, or SELinux that is, in the status row is enabled. And here you see it is. When SELinux is running, it mounts a pseudo file system like the proc file system, which is maintained in memory and manipulated by the Linux kernel at the mount point /SELinux when it's enabled. The mode is returned. This tells us that it's enforcing. In other words, if we attempt to break rules defined in the mandatory access control policy of targeted, then SELinux will deny connectivity. And we've seen some cases throughout our studies so far of SELinux interrupting the process of, let's say, HTTPD and others. And the mode from the config file, there's a primary config file located in etc SELinux, contains the option enforcing in this particular case, but can also contain permissive as well as disabled. The version of the targeted policy, version 21, this is the version that ships with Red Hat Enterprise Linux. The policy that's currently being used, or the name of the policy, is the targeted policy. This is the default supported policy, and it tells us the name as well as the version. So it displays current SELinux status, including policy name, let's just list it separately, which defaults to targeted. This is the supported SELinux policy within Red Hat Enterprise Linux, meaning there are other policies, for example the strict policy which you can install, but it isn't supported and requires an advanced understanding of SELinux to implement. So the policy name, policy version, the version that ships is 21, so if you make changes it'll be upgraded to a higher number version. In addition, the mode, which for our case is enforcing, but could be one of enforcing, permissive, or disabled. And let's return to the shell to see what other goodies are returned. The mount point and the SELinux status, which is expected. So use SEStatus to determine whether or not it's enabled. In addition, you can run SEStatus with the V option, the verbose option, which not only returns the information returned without the verbose option, but various contexts for different programs and different files. So for example, min-getty, which accepts connections, login connections on different TTYs, runs within the context system use, system R, so the system user, system role, and runs within the domain getty_t. These three fields represent the mandatory access control policy fields, the key fields processed by SELinux. Two of the three, the user and the role, are not heavily used with Red Hat Enterprise Linux. The third, however, the domain field, is very important as it tells us whether or not a subject is within its own confined domain or within the all-purpose unconfined_t. So for example, init, which is the first user space process after the scheduler, so process ID number 1, has launched using system U, system role, but we can ignore system U and system R or the user in the role fields until they become more important, perhaps in subsequent versions of Red Hat Enterprise Linux. Init runs within a special context known as init_t. So init is jailed into its own domain, its own sandbox, and can only access files or objects that the init_t domain is granted access to using this mandatory access control system. So it's a way, again, of sandboxing subjects and objects, whereas in standard Linux permissions, discretionary access controls, a user can roam the whole system and interact with files in a way that you may or may not want them to. min-getty operates in a separate zone, or in a separate domain, getty_t, meaning the min-getty process, which is tied to the various TTYs, will not be able to interact with the init_t process. And we also see below other domains, such as shadow_t for the etc shadow file, and others. So the verbose option zeroes in on key files, key processes, or key subjects and key objects. Files are objects, processes and users are subjects. Now let's list another important file, and that's the main configuration file, which is accessible in two locations. Its primary location is beneath etc SELinux, but on your RH5 box you'll find a link to it in etc sysconfig SELinux. This is the primary startup config file for SELinux. When your system boots, it reads the contents of this symlink, which points to the etc SELinux config file to determine whether or not to enable SELinux and at what level. So let's take a brief look. We'll LSL the full path, and where you see it points to etc SELinux config. So if we examine the contents of etc SELinux config, we'll see it's brief. Determines whether or not SELinux is enforcing, disabled, or permissive, and the name of the policy that is to be loaded when the system starts. It is in enforcing mode, and the targeted policy is the default supported policy. An LSL of etc SELinux reveals various options, including config, which is the config file, a context file to help restore contexts on different objects, an SEManage configuration file, which the SEManage utility uses, and a subdirectory tree for the targeted policy. So you can find information regarding the targeted policy beneath etc SELinux, and as mentioned, this is the targeted directory. So targeted is the top level container for the targeted policy, which includes everything such as the binary, which the SELinux, the binary for the policy, and ancillary files. Now let's take a look as one of our tasks. Again, this is only an intro to SELinux, so we're not going to delve deep in. We just want you to see how it impacts your system, how the targeted policy impacts your system, and how to maneuver around SELinux. Let's restart Linux CBT Serve for disabling SELinux. So task 1, disable SELinux upon boot up on the server Linux CBT Serve 4. And to do this, we'll modify grub.conf. So we'll nano etc grub.conf, which is really a symlink to boot grub, the menu file. Let's go ahead and execute our nano process, and we'll modify the kernel line, appending the appropriate SELinux command. Here we can determine whether or not it's in enforcing versus permissive versus disabled mode altogether. If we simply indicate SELinux equals 0, this turns off SELinux when we reboot it. No mode is necessary. This setting passed into the kernel overrides etc SELinux config, or etc sysconfig SELinux. Again, we're passing it directly into the kernel. So if there's a problem, if you need to debug, if you need to make some changes, if you can't determine why SELinux is blocking communications with your system or various areas on your system, you can always reboot the system and disable SELinux. Let's save the changes and then reboot the remote system. And when we return, or when it returns, we'll see that the SELinux status returns disabled. So we've modified etcgrub.conf. Then we've updated or update kernel line to reflect SELinux equals 0. This disables SELinux very simply on the remote system, and a reboot will ensure that it doesn't come up. And while we're on the topic of disabling SELinux during reboot, let's also note that there is a tool, SETInforce, that you can use to enable or disable the mode of SELinux when it's up and running. In other words, you can change or alternate between permissive and enforcing. So SETInforce, for example, setting it to 0, enables the permissive mode, which again keeps SELinux running but does not deny access by various subjects to various objects across domains, or from subjects to objects that typically would not be allowed when SELinux is enforcing. And if set to 1, then enforcing, which is was the current mode, will be the default. Now now the remote system should have rebooted, so let's reconnect. And it appears to have. We'll execute an uptime. It's been up for a minute. And then SE status will tell us that it's currently disabled, which means we can switch between domains or interact with different objects as different subjects without any repercussions. And now that we know it's disabled, if we go ahead and execute PSEF with the uppercase Z option, we won't see any SELinux context information for any of the processes that are running, which leads us to another point. Dash uppercase Z can be applied to the following tools to obtain SELinux context information, including but not limited to MV, CP, LS, as well as PS. Using these tools, you can determine contexts on any SELinux enabled system, not just Red Hat Enterprise. Even for our local system, if SELinux is enabled, a PSEF-Z will return context information. As we can see, it's not on the local system. Let's go ahead and set the server to re-enable SELinux by modifying boot grub.conf and setting SELinux here to 1, or removing it altogether, causing init when setting up the kernel to read the contents of etc SELinux config, which includes that SELinux should be in enforcing mode with the type targeted. You should also note that when your system is not running SELinux, the mount point contains none of the information you'll find on a running system. So there are no files pertaining to the current status of SELinux as it's represented in the kernel. Again, just like the proc file system maintains current running items in the kernel pertaining to all aspects of the system, USB, networking, so on and so forth, the /SELinux mount point is like proc in that it's in memory and it maintains directives and values and caching information for the loaded policy as it applies to SELinux. So again, let's reboot the system. The clean way to re-enable SELinux is to reboot. You can do it without rebooting, but it is the clean way. Or you may bring up your system with SELinux enabled, but set the enforcement to permissive to allow the normal behavior of the system, that's discretionary access control behavior of the system, to proceed. And we did mention that the tools LS, CP, MV, as well as PS support the uppercase Z option. That option is reserved to return SELinux related information. When you run it when SELinux is not enabled, you do not see that contextual information. In other words, the system user, system role, or SELinux user, SELinux role, as well as the type or the context. When it is running, however, you do see it, and you can influence the type by changing it using chcon, which is another utility that we'll list. And let's go ahead and just indicate chcon R followed by T and the type followed by file applies label, and that's an SELinux label, to file and optionally directory or directory container and all of its contained items. Now just a quick note here. If, for example, you navigate between permissive and disabled, or files have lost their context, so note if files or objects lose their SELinux context, there are multiple ways to relabel them, including but not limited to one, simply touching at the root of the file system prior to rebooting an SELinux file auto-relabel, which causes SELinux when it boots to appropriately apply the policy, the targeted policy, to all files in the file system. So by touching / a hidden file auto-relabel and then rebooting the system, so ampersand using the ANDing, logical ANDing, init, this causes init to relabel the system according to the targeted policy. This is the clean way, the suggested way of relabeling files. Touching auto-relabel and rebooting the system. When init initially starts, it determines whether or not SELinux is to be supported, and if it is to be supported, it confirms the different domains, sets them up, but if it finds the auto-relabel file, a hidden file, it will apply the labels defined in the targeted policy. Another way is to use the fix files utility used to relabel while the system is running, and used to relabel objects, that is. And by objects we mean, obviously, files. Of all types, of course. So use fix files as another means of relabeling items on the system. Now before we confirm that SELinux has been enabled on Linux CPT Serve 4, let's just note list of daemons, which is included in the documentation for Enterprise Linux 5, Red Hat Enterprise Linux 5. So a list of daemons protected by the targeted SELinux policy includes but not limited to Apache, which within Red Hat is implemented as HTTPD, the Dynamic Host Configuration Protocol daemon, DHCPD, NTPD, the DNS server, named, syslog, squid, the proxy server which we looked at briefly, SNMPD, Simple Network Management Protocol, as well as port map, which is used for RPC services such as NFS, services that require ports to be dynamically allocated, as well as the name service, caching daemon, and winbind. These are the major daemons protected by the targeted SELinux policy, which means each daemon has its own sandbox and cannot encroach upon the other daemon's sandbox. Apache cannot interact with DHCPD, which cannot interact with NTPD, and vice versa. However, in addition to the list of daemons, note, we'll mention again, the targeted policy assigns all other subjects and objects to the unconfined T domain, which means those subjects and objects will be treated just as they are in a standard discretionary access control based Linux system. In other words, a Linux system with no SELinux installed. Let's reconnect. And once on, we'll execute SE status, which will tell us that it's enabled, which also means in SELinux, the various files, including the advanced vector cache, which contains the cached policy items for the targeted SELinux policy as it applies, which is consulted by the kernel whenever a subject attempts to access an object. Booleans, which control various daemons and how they may interact with different items, and there are booleans for the protected daemons, including, of course, HTTPD, which gets set, such as whether or not Apache may connect to a database versus to the network versus relay or trans or climbing through the directory trees and others. So that mount point is up, SELinux, which tells us that it's up and running, which means now when we reset the buffer and rerun PSEF upper Z, we see on the left the context information for the different daemons. Again, init is in its own jail, its own domain. The kernel is running certain processes in its own jail or domain. And if we scroll through this list, we'll see many other domains, such as the domain for HTTPD. That's PSEFZ, grep HTTPD, and we see Apache runs within the HTTPD_T domain. Well, what does this all mean? Well, providing that Apache is married to or belongs to the HTTPD_T domain, it will be able to access components of the system, in particular objects, granted to the HTTPD_T domain, or type. So type enforcement binds the domain that a subject belongs to the type that an object belongs to. So let's just note that the default SELinux targeted policy using mandatory access controls binds subject domains, and we'll just indicate, i.e. HTTPD_T, to object types, i.e. HTTPD config T, and others. Case in point, let's navigate to the shell. We'll navigate to etc, then lslz, upper Z, the HTTPD directory where we see, and let's add the D option so that we can focus in on the directory. We see that the directory belongs to the user and roles that don't matter to us for our intents and purposes with working with the targeted policy. However, there's a type that's associated with the directory, HTTPD_config_T, and SELinux enforces mandatory access controls providing or permitting the various HTTPD daemons located in the domain HTTPD_T to enter the type HTTPD_config_T. So by SELinux's mandatory access control rules, which compound the discretionary access control rules, so we need to ensure that the Apache user can actually enter the HTTPD directory. So on top of the DAC that's in place for this directory, SELinux allows this domain via the targeted policy to enter this directory and to subsequently interact with the files and or directories beneath that directory, which includes the type we just mentioned, as well as HTTPD_log_T. So it's this sort of granularity that SELinux provides, the ability to control access to the log files versus the config files, and to write policies which govern access to these items. For example, access into etc_T. Apache has to be granted this access to create a PID or a process ID beneath var run. So everything can be controlled, and it takes an awesome amount of time and know-how to write SELinux policies, but it's this level of control on top of DACs that makes SELinux so powerful. So one other note, SELinux MACs, or mandatory access controls, compound Linux discretionary access controls. So not only must the process or subject and or user have access vis-a-vis DACs to a resource, then SELinux also applies, or on top of that SELinux applies MAC. So the user must have access, or subject must have access DAC-wise, and be granted access MAC-wise if SELinux is enabled. Now again, there is a strict policy that's not supported by Red Hat, which you can find in the repository. We've set up our Yum repository. Search for our file here. We'll just go through the list. It's the development package. This policy development, by the way, provides source information for the targeted policy, but the SELinux policy strict package includes the strict policy, which jails every process or every subject into its own domain and forces you to assign types to all files on the system. So it's much more difficult to administer the strict policy, but it is quite possible, although not currently supported. As far as you need to worry about with respect to examination and just Red Hat's implementation of SELinux, it's the targeted policy, which protects the list of daemons we've mentioned and resorts everyone else to the unconfined T domain as a result. When you're logged in as a user, one other note, the ID command can also be run with the upper Z option, and it tells you the user. And there's a root user. This is a root SELinux user, a role, as well as the domain. So we see root belongs to the unconfined _T domain, and you'll see the same for other subjects on the system. So if we were to SSH as Linux CBT at localhost, let's try that, and then execute ID with the Z option, you'll see that also the user Linux CBT, who is non-privileged, belongs to this unconfined _T domain. So in other words, truly with the targeted policy, outside of the daemons that are protected, everyone belongs to every subject that is, and every other object, non-protected object, belongs to the unconfined _T domain. Let's just add ID to this list of commands. Now there's a lot more SELinux can do. Again, consult Linux CBT SELinux edition, although it focuses on Red Hat Enterprise 4. The concepts remain the same. SELinux has been in development for a number of years, and the mandatory access control behavior of it doesn't change overnight. Just the tools change, some items change. We do want to mention that there is an additional utility, the system config utility. We didn't show you that for SELinux. This utility allows you, if the GUI is available, we need to SSH in using the X option to control the default settings of SELinux on the box. Let's try it out again. That'll be system config SELinux. This will pop up the GUI for the tool on our box, and this allows you to set some things such as whether or not SELinux permits, disables, and forces. It reveals the current mode, so this is information gathered from SEStatus, or can be returned using SEStatus. Different policies, only targeted is supported. Whether or not you'd like to relabel on the next reboot, which creates that auto relabel file we've mentioned. Different booleans for different services. Again, these are the protected daemons, and they're booleans that you can enable or disable using this GUI, such as allowing Apache to use modauth PAM, allowing Apache to be a relay, and other things that you may want to take a look at, such as traversing directories, etc. File labeling, another interface which allows you to set, essentially this SELinux utility is a quasi-policy administration tool. So this is showing us information from the targeted policy, how different directories are labeled, such as the temp directory being labeled temp T, which it doesn't show up as default, but you can impact the label by modifying the properties of a given directory. User mapping, how local users map to SELinux users. Another thing we haven't mentioned, that SELinux maintains its set of users distinctly from Linux users. And here we see the default users, root, system U, and user U. All of the users minus root on the system belong to system U and user U. Various translations, network port access, and the policy modules for different plugins. So this utility gives you some way to manipulate your SELinux setup. Not a major utility, or not many of the options can be changed, but some options can be changed, as opposed to having to remember which files to update. So hopefully we've introduced you to how SELinux is implemented on your Linux system with Red Hat Enterprise 5. In most cases, you'll find that the implementation, the enabling, the enforcement of SELinux will have no impact on the processes that you're running. But if you do see an impact, then you know to consult varlog messages to determine if there's anything in your way or anything you need to do, such as enabling a boolean, so that using the appropriate tool, the set SE bool tool, so that your system can behave as expected.